Sylvia Ekström, and she will give a review talk on stellar evolution and metal-poor and metal-free stars.
Thank you. 5 minutes, yeah. Do you hear me? Yeah? That's OK, thanks. So let me first thank the organizer for inviting me today. It's very significant for me because the third opus of the First Stars conferences in Santa Fe was among the first conferences I attended when I was still a baby astronomer. So it's very nice for me to be here today, giving an invited review now in this fifth opus. So we want to understand the evolution of metal-free and metal-poor stars. And we heard this morning that we are starting to observe population 3 signatures in galaxies, in high redshift galaxies. And actually, I would tell you that this is a very bad news for us, because just until now, we could model population 3 stars happily and freely without any observational constraints. That was great. And now things are going to change. We will have to confront our models to real observations. And that's promised to be quite challenging, probably. So we want to model stars, and for this we use our favorite structure equations that we use also for any other kind of stars. And probably the most striking difference is we rely on this little kappa term there, the opacity, which will be, of course, much lower for low metallicity stars. Because of this low opacity, we expect these stars to be very compact, with a very short radius. Here you see a plot of the radius of the star at the ZAMS for different initial masses. And you see for different metallicities. In dark blue, you have the solar, the old solar abundances. Light blue is SMC. And then in green, you have a very low metallicity, but non-zero. And in red, the zero metallicity. Mark the color code, because you will find it again in my talk later. And you see that for any mass range, the low metallicity drops the radius, the external radius. It's always very, very low. So we have a short radius. We have also a very hot cores, because, of course, the star has to contract much more when it forms to get the energy it has to sustain itself. So we expect large changes in the Archer diagrams, depending on the mass. And you see that from the solar metallicity models to the zero metallicity models, there is always a shift towards higher temperatures. It's about a factor of 2, a 0.3 index. And you see that also the shape of the tracks are slightly different. In the interior of the star also, you expect large changes, since the star, as I mentioned, had to contract much more to get its energy when it has only little metals. So you see that the ZAMS is shifted towards much higher temperature, central temperature, and higher densities. In the 9 solar mass, we see a very interesting feature here. It's this little hook there that marks, actually, the moment when, for these zero metal models, the CNO cycle is ignited. It is not ignited on the ZAMS. The star has to contract much more until it creates enough carbon to trigger the CNO. And the CNO starting there makes this little hook there that you see also here in the 3 solar mass star. The more massive stars make CNO right away. They contract directly to the point where they create carbon, and they can ignite the CNO cycle to sustain them. Here I show you the size of the cores of different masses, and still with different metallicities. And you see here that, well, in general, you can see that when you lower the metallicity, the cores are higher than at solar, except zero metallicity. You have a change of regimes when the metallicity drops so low. And here you see that the moment the CNO cycle is ignited is marked here by this bump in the size of the core. The cores at zero metallicity are really much lower, because much smaller, because the opacity is smaller, of course. So the medium can remain radiative even at higher temperatures. Now a word about rotation. You heard already this morning that we expect those stars to be rapidly rotating. And first of all, we have to look at the critical velocity. When we express the critical velocity, we see that it behaves like the square root of the mass over the radius. And so at low metallicity, you expect smaller radius for the same mass, for a similar mass. And so you expect a higher critical velocity. Here you see the critical velocity on the ZAMs, again for different masses and for different metallicities, solar there and zero here. And you see that actually, when you plot this, the critical velocity for solar metallicity for a solar star at 60 solar mass star would be around 800 kilometers per second, while the same 60 solar mass star at zero metallicity, it would be over 1500. This is a very important why, because it means that you can get a much faster rotation and still have an average ratio to the critical limits. Here we plot the velocities, the initial velocities for 20 solar masses with this average ratio of the surface velocity over the critical velocity. And we see that to get this ratio at solar metallicity, you need a little more than 300 kilometers per second, 340. But if you go down to zero, or even to zero metallicity, you need to go higher than 600. And I recall that all the effects of rotation depend on this ratio, not on the velocity itself, but really on the ratio to the critical limit. So that was the initial conditions for the stars, and now we want to understand how it will evolve through times during the life of the star. And for this, we need to transport this angular momentum in a way or another. And we use usually these equations where you have a diffusion term, but you have also an advective terms where you recognize here the meridional circulation effect. I just mentioned here that for the chemical species, when we want to look into the mixing that is driven by rotation, it has been shown that a purely diffusive equation is enough. So there is no advective term in the diffusion of chemical species. So this meridional circulation term is very important for the transport of angular momentum. And here you see that in the outer cell of the star, it will behave roughly like this term, with this mean density down there. So it means that for normal metallicity stars that have quite diffuse envelopes, this term is low, so meridional circulation is largely negative, I would say. But then, when you go to lower metallicity, this term becomes high, and so it weakens a lot the meridional circulation, the strength of the circulation. Because of this, you expect that the internal profile of your rotation will be much steeper. And here you have the evolution of the solar metallicity star, that so at the beginning, more or less the beginning of the main sequence, the middle and the end. And the same for the SMC star, and then for 10 to the minus 5. And you see that the gradients are much stronger in that last case. The evolution of the velocity itself is very dependent of two processes. It's really an interplay between the winds and the transport. So the winds will break the star, it will remove some angular momentum from the star, and the transport will probably accelerate the surface of the star by driving the internal rotation of the core to the surface in a way or another. Now, both aspects are very dependent on the mass and on the metallicity. Here you see a 20 solar mass model. It's all the same mass and it's the same ratio at the beginning. And we see how the velocity behaves when you compare it to the initial velocity. Of course, I put that because otherwise the curves would not start at the same place and it would not be so clear to see what happens. And you see that that is what you expect at solar metallicity, a rather flat main sequence, more or less. And when you go to lower metallicity, you see that, on the contrary, it increases. Why that? Because when you lower the metallicity, you diminish the strength of the winds. The winds are weaker, and so you expect this to occur. The transport is also weaker, but the effect of lowering the winds are stronger, and so it increases, the velocity can increase during the main sequence. While once again, at zero metallicity, you see a change of regime. It's really different. When you remove all the metals, you also really make the meridional circulation so weak that this time the velocity evolves almost just by conservation of angular momentum. And so since the radius increases during the evolution, you see that the velocity decreases. Now we saw that the critical velocity is dependent on the mass over the radius. And so we expect also the critical velocity to change during the main sequence. During the evolution, with the winds, you will reduce more or less the mass, and the radius will increase. So the critical velocity is expected to decrease. And so even with a flat velocity, equatorial velocity, the fact that the critical velocity is decreasing will make this ratio increase. And this can occur in such a way that a star might encounter the critical velocity. Actually, the surface can be accelerated, not accelerated, but the ratio can increase such as to reach the critical velocity. Here I show you a plot where I draw, actually it is the value of the hydrogen at the center of the star when the star meets this critical limit with its surface rotation. You see this purple magenta lines are stars that have started their lives with a ratio of the critical velocity, the surface to the critical of 0.9, and these started this their evolution with 0.95. So it's very rapid rotators at birth, and you see that they meet the critical limit still during the last third, I would say, of the main sequence. But you see that at solar metallicity, the largest masses that have weak but still have some winds, the winds are sufficient to remove the angular momentum, so they don't meet this critical limit. While at lower metallicity, you see that the limiting mass to reach the critical limit is pushed toward higher masses, and at the SMC metallicity already, you see that even the 15 solar mass, for example, that did not at all meet the critical limit at higher metallicity, this time it meets it for the fastest rotator. When you talk about rotation, you expect, of course, mixing inside the star. And of course, when you have a very steep omega gradient, you expect the mixing to be strong. And at low metallicity, you also have a short diffusion time, because the diffusion time is roughly the square of the radius over the diffusion coefficient. And the star is very compact, so you expect a short diffusion time. So You expect mixing, and you expect it earlier during the main sequence than for a higher metallicity stars. And that's exactly what you see here. Here you have a kind of temporal axis where you see the value of the central hydrogen that goes towards 0 at the end of the main sequence. And you see the ratio of nitrogen over carbon compared to the initial one for different 20 solar masses models at an average rotation rate. And you see that the ones at 10 to the minus 5 in metallicity increases its nitrogen very early in the main sequence. Almost immediately when it starts, it's already enriched. Sorry. So this very strong enrichment, this very strong mixing can be seen on this plot. For example, for a grid of models by Ceci last year, where she modeled stars at the ITSWiki 18 metallicity. And you see here different tracks for 10, 20, 39, 77, 150, 294 solar masses with different velocities, initial velocities. And so you see that the most rapid rotators, they don't evolve at all towards the red like usual models. They directly evolve toward the blue. They are what we call them chemically homogeneous models. They follow a chemically homogeneous evolution. And for higher masses, the transport is much more efficient, and so you need even a lower rotation can start to evolve bluewoods of the ZAMs. So you expect, at low metallicity, you will expect to find stars in the blue part of the ZAMs, not only in the red part, like for more metal-rich environments. This has been found as well in population 3 models by Sungchul Yoon in 2012. He has exactly the same kind of behavior. The slowest rotators behave normally towards the red, and the fastest rotators goes with a quasi-homogeneous evolution. Here you see that the 10 solar mass star does not. They all go to the red, but for higher masses, it's stronger and stronger, and for even lower rotation, they would evolve towards the blue. Of course, we always rely on the physics we put in the models, and I encourage you to see the poster by Timothy Lawlord, the P2.9, where he shows that the convection, the way you treat convection, which criterion you use for convection, can change a little bit this picture. When stars are extremely blue and they have very high luminosity, you expect them to be sources of ionizing photons, very hard ionizing photons. And here it's a plot again from Yoon et al., where you see the difference of the number of ionizing photons emitted by rotating models compared to non-rotating ones. And you see that even at 20 solar mass, even 20 solar mass models show a very enhanced emission of ionizing photon compared to non-rotating ones. Something that can happen also is that because of the mixing, you have some. We are here in the situation where the star has finished his main sequence and is burning helium in the center, and there is a hydrogen shell here. And in population 3 models, the hydrogen shell is usually radiative because it's very weak. It's only triggered by pp change. But then, because of diffusion, because of mixing, you can have some carbon that is produced by the helium burning core that can reach the hydrogen shell. And when it does so, it suddenly triggers the CNO cycle inside the shell. And so you have a flash occurring. The shell becomes convective. The luminosity, the energy generation jumps from about 3 orders of magnitude. It almost shuts the core. And then the profile settles back to a more normal core and shell, convective core and convective shell profile that we are used to in normal metallicity stars. This is very interesting for us because this will really boost the nitrogen production in the shell. And when you have a high production of nitrogen in the shell, of course, you had some carbon coming from the core to the shell, but you can also have some nitrogen coming back from the shell to the core. And this is what happens. And so here you can look at the profile of the stars. You have here a 40 solar mass star population 3 model. You have the internal layers. This is the internal mass with the surface here, the center here. And here you have the mass fraction of the elements. And here it's for a non-rotating star, and here for a fast-rotating star. And you see that the fast rotators has undergone this flash and has produced a large amount of nitrogen. And this nitrogen will go back to the core to form neon 22, which is here in dotted red, the dotted red line here, which is totally absent here. And so the neon 22 is very interesting because it's a seed for S process. Yoon et al. Have a different physics in their models. They do not have these flashes, but still their fastest rotators, the yellow dots here, meet the same amount of nitrogen production that my models, because of this chemically homogeneous evolution, actually. Now, if you can make S process, you can maybe find it in halo stars, and that's what Chiappini et al. Have looked at. They have tried several models of galactic evolution to look at the yttrium over baryon ratio, and they have shown in this paper in Nature that the S process material of very massive, very fast rotating stars is able to reproduce the scatter, the large scatter that you can observe at low metallicity of this ratio. I will not go further in the nucleosynthesis domain, since Alexander Heger will give the next presentation about this, and you will hear lots of talks about nucleosynthesis. It's not my role to talk about this. Now, of course, we can look at the final state of our stars. We want to know what fate expect them. So if you look, first of all, one very important notion for this is the final mass that the star will have. And you see again at high metallicity, the winds remove a very significant part of the mass. Here you have, for example, the rotating 120 model finishes its mass with less than 20 solar masses. So it's the neutron star domain. While at lower metallicity, the slopes are closer and closer to the slope 1-to-1 because you have less and less mass loss. Except that with rotation, you might reach this mechanical mass loss. This when you reach the critical limit, some mass will be shed, and so you expect the rotating models to have still lost a little mass during their lives. I show here a very known plot by Alexander Heger and collaborators, where you see here you have the metallicity from 0 to about solar here, so going up here, and here you have the initial mass, and you see what kind of fate expect the star. So when the mass is low enough, you will have just a neutron star, or if the winds are high enough, so at high metallicity, even high mass stars will lose enough mass to be in the regime of neutron star. And then you will have the black hole domain by fallback, and then direct black hole for lower metallicity and higher masses. Now we can interest us to the really metal-free line. If we look at this line there, that is what Sung-Chul Yoon has done for population 3 stars. But he has varied the rotation rates, and look what happens. What do you expect as a final fate for these stars? And you see that the picture is quite diverse because of this rotation rate that can change quite a lot the picture. But you see that there is a very interesting regime here where you can make GRBs progenitors. You are in the high rotation and sufficiently high mass to trigger GRBs in a hypernova event. Otherwise, you might have direct collapse into black holes, and again, a small region where you can have pair instability supernovae that will disrupt the whole star completely. Now, a word about binarity. You have heard this morning again that the cloud of star formation can fragment, and that some binaries can be made, or at least multiple stars can be made. In the solar neighborhood or in the LMC, it is well known that when you observe a single star, what you think is a single star, it has only half a chance to be real single. There is a strong probability that it is the result of a merger, 20% chance, or that it's just a companion after a mass transfer that you are observing, or it's just a pre-mass transfer binaries where you don't see the binarity. While when you detect something as a binary, it can be several flavors of what happens in a binary life. So what would happen at low metallicity, real low metallicity? I show you here 2 plots that have been done, we have done with Hangfeng Song last year that we have published. So we have modified our code so we can follow the tidal interaction inside the star, the tidal interaction that would be triggered by a companion. And you see that we have varied the period from 1.4 to 1.8 days. And we have varied the initial mass of the primary. Here we have always taken a secondary that which mass is a third of the initial one. And you can see here it's solar metallicity, here it's more or less LMC, and here it's SMC. And you see that the Roche-Lobe overflow event is different depending on the metallicity. While at solar metallicity, most of the stars, most of the time, the primary goes through a Roche-Lobe overflow during the main sequence already, and only in some conditions of the highest mass and the longest period, there is no Roche-Lobe overflow. While at lower metallicity, what happens? The stars are much more compact. So even for a short period, they will be farther apart, I would say, than for a higher metallicity because the radius is smaller, and so they don't undergo so much mass transfer. They don't fill their Roche-Lobe with the matter, even if they do not show an homogeneous evolution during their main sequence. We see that sometimes. Of course, if it's homogeneous, you more or less expect no Roche-Lobe overflow. But even with a non-homogeneous star, here you have no Roche-Lobe overflow. So very low metallicity binaries might avoid some mass transfer that we could expect in higher in higher metallicity stars systems. Okay, I will finish there with my summary. So when you lower the metallicity, you get extremely compact stars. They are very blue. They are hard ionizing photons emitters. They might also rotate fast. You expect them to rotate very fast. They might reach the chemically homogeneous evolution. And they can shed mass through mechanical mass loss, even if their winds are weak. And so they might lose some mass. They are also probable gamma ray burst progenitors, and I'm sure we will hear a lot about this later in the week. They might trigger pair instability supernovae as well. and we have yet to study carefully the behavior of multiple systems. Thank you.
Thank you, Sylvia. Thank you for this beautiful review. And we have time for questions.
So if I understood correctly, including rotation leads to a higher mass loss for the low metallicity stars. So does this mean we have to revisit our POP3 black hole seeding scenario and push down the masses for those black holes, or those are unaffected?
No, I would say, you know, it loses a little mass, but it's not dramatical. It's not. I think it's maybe it shifts a little bit the frontier between black hole or no black hole, but it will not be dramatic. Probably not.
I guess that the main problem is that you also shift the per-instability regime, where you disrupt the whole star. So
yes,
then this may have larger effects.
Can you go back one more slide, the previous slide? So you mean the binary which explains the Roche-Lobe overflow, I mean the low metallicity case, so should experience the homogeneous evolution?
Some of them will experience homogeneous evolution because of the tidal mixing. You know,
so this paper only considers tidal spin up.
Yes, it's because of tidal forces.
Okay, what about the zero metallicity case in this plot?
It's not there because we didn't model them, but we plan to do that. Probably it will be, my first guess like that is that they would never have any Roche-Lobe overflow, at least not at all during main sequence, and probably not during helium burning, because usually they burn helium still in the blue, because they evolved from main sequence to helium burning at the same place in the HR diagram, since they burn already helium during the main sequence. So my guess is that they will not cross the HR diagram, so it will be very difficult for them to fill their Roche-Lobe. But we still have to model this. For the moment, we modeled only with metals, and we are now starting without any metals. So stay tuned.
Okay, thanks so much.
Thanks.
I think we have Stefania first, and then Kazu.
Thanks. So I'm interested in this shift of the per-instability regime. Can you actually quantify that or give some reference? Because the impression is that the higher is the mass of metal-free stars, the lower is the effect of this mass loss. Okay? So how much it will be shifted? Usually it's from 140 to 160.
Yes, I cannot answer you like that. If you look at Yoon's paper, he shows a diagram where he shows that you can hit the per-instability regime even with a lower mass.
About 100.
But about 100 or?
About 100
yeah.
from their
still,
diagram.
Yeah, it's still more than 100.
Okay,
yeah.
Thank you.
I have a very basic question. So I'm interested in the angular momentum transfer inside the star.
Yes.
So what is the physical mechanism to that, and how it is well known or calibrated?
So we calibrate it at solar metallicity or solar neighborhood metallicity, and we consider that the physics is the same at lower zero.
What is the physics?
The physics is the equation I showed you.
Yes, so you showed the diffusion or something, and so what is the physical process to transfer the angular momentum? Is it by convection or some?
No, it's by rotation. So it's the shear and the meridional circulation. Shear mixing and meridional circulation.
Okay, and so you said for solar metallicity it is calibrated, but by what kind of observations?
We calibrate first the efficiency of the mixing with observation of the nitrogen abundance in the B-type stars.
Yes.
And then for the efficiency of the velocity of the angular momentum transport, it's difficult. We use the same parameters that we used for the enrichment because it's difficult to really observe the velocity of stars of OB stars, of O stars at least. And so we rely on this efficiency. We calibrate the efficiency of the mixing And we use the same thing for the angular momentum. It's the same diffusion for the angular momentum.
Okay, thank you very much.
You're welcome.
Daniel, William?
I just wanted to make a quick comment going back to rotation and how it moves the lower mass limit for parent stability events. And there are recent multidimensional simulations by Manos Achopoulos and Craig Wheeler at Austin that show that if you have rotation, it can actually drop the lower limit to about 90 solar masses.
Okay, thanks.
It's because of the rapid buildup of the core, but those explosions will look very different than the 140 to 260 solar mass events because the rotation drives off the hydrogen layer.
Probably,
So,
thank you.
They will look different, but it will disrupt the star anyway, right?
Completely. Although we found in another paper, if you're at metallicities of about 0.1 solar, parent stability events actually can produce black holes.
Wow.
Any other question or comment for Sylvia? If not, we should go for coffee and reconvene again in 30 minutes, and thanks Sylvia again.